we go.
Well, she's on, I guess.
Yep. I think we should be good now.
All right. So, do you want me to start, or is there anything you wanted to say at the beginning, or?
No, I don't think so. I mean, the only thing I would just make a note to everybody is we'll be sending out the announcements for the July research webinar probably sometime later this week. So just keep an eye out for that.
All right. Then I will start. Chris tasked me with running today's webinar, so I had no choice but to agree. So welcome, everyone. Good morning. Good afternoon, depending where you are. Today we have two talks. They are going to be roughly about 20 minutes in length, with some time for discussion and question and so forth. So the first presentation is titled Unveiling Synergistic Effects of Nano-Modification and CO2 Curing on the Durability and Carbon Footprint of Precast Elements. And this is going to be done, the presentation is going to be done by Ms. Aniya Edwards. She is a first year master's student here in Materials Group at Purdue University. She actually started working on research as a senior with Professor Velay, who is also in line and is a PI for the project that Aniya is going to be presenting. And Aniya interest is in environmentally friendly materials and improving infrastructure sustainability. She also works on recycled materials. So without further ado, I will turn it over to Aniya.
Hello, everyone. Can you hear me?
Yes, we can hear you.
Okay, good. Just making sure everything is in order. So let me go ahead and share my screen and we can get started. All right, so as you all have heard, my name is Aniya Edwards, and I will be presenting to you unveiling the synergistic effects of nano-modified or nano-modification and CO2 curing on the durability and carbon footprint of precast elements. My name is Aniya Edwards, and this is under the advice of Professor Velay, Professor Olek, and Dr. Tokpatayeva. Before we start, I'd like to go over a general overview of what I'll be presenting today. We're going to go over the motivation and background of this project and the background on some of the materials that we'll be using. Then we'll go over our objective for this project. We'll go over the characterization of the materials we'll be using, along with the methods that we've used to move this project forward. And then we'll go over some of the results and the analysis of some of the results that we've gotten thus far. And then I'd like to conclude it with some of the future steps that we hope to complete within the next couple of months. So as we all are pretty much aware, for those of you who are not aware, the concrete life expectancy ranges from about 50 to 100 years. And since most of our infrastructure was built during the population boom between the 1920s, 1930s to 1970s, we're approaching the end of that lifespan for a lot of the concrete elements that we use in our infrastructure. So because of this, new infrastructure demands require that we improve our durability to help make those concrete elements last longer, while also reducing the carbon footprint so that we are more environmentally sustainable. With the precast industry, it's particularly favorable because it allows us to meet a lot of the production demands and meet those supply requirements that we have for concrete elements. And there are different treatments that we use in the precast industry to meet this improved durability and reduction of carbon footprint requirement. We're evaluating two different aspects here. One is nano additives and the other is curing treatments. So one happens during mixing, the other happens while curing. And under the nano additive umbrella, we're going to be evaluating carbon black and nanosilica. And then for curing treatments, we're going to be evaluating CO2 curing. So background on nanosilica for a bit, it's a really hot topic in the civil engineering industry right now. So nanosilica is pure silicon dioxide for the most part, and it's a key component in pozzolanic reaction. When silicon dioxide reacts with water and other concrete compounds or cementitious compounds, then it can result in the development of CSH. And CSH is one of the primary components, strength contributors in concrete elements. When using silicon dioxide, so when adding that to our cementitious mixtures, we can improve the overall strength of our mixtures, and we can also accelerate the final setting time and reduce the porosity by increasing the amount of CSH gel that's in our composites. However, this depends on multiple factors in regards to the nanosilica. One of these is particle size, another is particle distribution, curing conditions, water to cement ratio. In fact, in one 2019 study, as shown on the left, it was evaluating the influence of particle size on the overall development of CSH gel and the microstructure of cementitious composites. And it found that if you use too fine of a surface area for nanosilica, you can actually result in agglomeration, and that can result in further cracking. Whereas without nanosilica, you can see some microcracking in the image A in the top left corner. So there's a sweet spot for what kind of nanosilica you want to use and what kind of surface area you want to achieve. And for them, it was found to be 50 to 250 meters squared per gram. So along with this, there's a lot of other factors. So it's a very multifaceted material that we're looking at when it comes to using it in concretes. Then we have carbon black. Now, carbon black isn't as nearly as popular when used in cementitious mixtures. It's quite recently developed some fame. For those of you who are not aware, carbon black is pure carbon for the most part. And the way we acquire it is we use some type of hydrocarbon form. So usually things from the oil and gas industry. We confine it in a space and heat it up to really high temperatures. And from this hydrocarbon, you'll get a plume of black dust. And these black dust, the black dust that we see in it is very, very fine. It can reach the nanoscale. And that's the carbon black that we're getting from these hydrocarbons. And in turn, that can result in an additive that we could possibly add to our cementitious mixtures. Carbon black is shown in different studies to improve strength, densify the structure of the composite, and it can be electrically conductive. In fact, carbon black has been used with graphene, carbon fibers, other steel fibers to create a sort of framework within the cementitious composite. And that can in turn be used for smart sensing concretes. Just last week, there was an article posted on an MIT study where they actually found carbon black to be a sort of supercapacitor that can be used to conduct electricity through a cementitious composite. So very interesting there. So the objective of our project is to understand the synergistic influences of nanomaterials and CO2 curing on the hydration and strength development and other facets of cementitious composites. So what we're trying to see is how do these nanomaterials and using these nanomaterials influence the cementitious composite with the combination of CO2 curing. So the two materials, as I mentioned, we're using nanosilica and recovered carbon black. For carbon black, the recovered carbon black that we're using, so instead of carbon black being attained from hydrocarbons, we're actually going to be using recycled products that have carbon black. It's mainly rubber, so rubber waste tires or black rubber materials that have carbon black in it. What we should know, however, is that carbon black is a natural agglomerate. So there are different size categories to classify what carbon black actually is. When looking at the TE image shown on the slide, you might think that, oh, well, it's not a nanomaterial because this large agglomerate piece obviously exceeds the 100 nanometer range. But we have two different size categories: aggregate sizes, which is the overall agglomerate structure, and then we have the primary sizes, and those are the little orbs highlighted in the red outline. And that's the nanomaterial that we're referring to, which is what makes carbon black an inherent nanomaterial, because these little red orbs are the outline structures of the carbon black nano primary sizes. Another thing to note is that carbon black is extremely hydrophobic, so it does not mix well with water. As you can see in the video, carbon black kind of sinks to the top or sinks to the bottom of the water, or it floats and forms a film on the top of the water. It does not well disperse through the overall water bubble that we see here, and that's very important when it comes to concrete mixing, as we'll see in some later slides. Another thing to note about carbon black, so we're using recovered carbon black, or RCB. We have more pure carbon black, which comes from those hydrocarbons that I mentioned earlier. And when doing a loss of ignition test, we heated up our 2 different carbon black samples at 900 degrees Celsius for 3 hours. And what we found was that the more pure carbon black completely disappeared after that heating. So that shows and affirms its purity, whereas the less pure carbon black, which was made from the waste tires, has impurities left over, not necessarily carbon. After doing some XRF testing, we found that it was sulfur and other inorganic compounds, but that kind of proves just how impure it actually is. However, we still decided to go with the recycled carbon black for our mixes because compared to the pure carbon black, which is about 95% purity, the recycled carbon black is less expensive and it's more environmentally friendly. So we're really trying to affirm that environmental sustainability aspect. And then for nanosilica, what we're using is an aqueous nanosilica solution. The image here is actually the nanosilica solution after being heated. So all of that water has evaporated from our solution. But if you can see in this TEM image, you can see that there's a homogeneous dispersion of the nanosilica particles. So it's not nearly as easily to agglomerate as the carbon black. Nanosilica is actually commercially used in a lot of DOT projects. There's a few standards regarding the use of nanosilica in certain concretes. So it's really easy to incorporate in our infrastructure. And the sizes, the particle sizes of nanosilica that we're using ranges from about 10 to 90 nanometers in diameter. So the methods and mix procedures. So what I will be showing to you today is the mortars that we're going to be mixing at 0.42 water to cement ratio. We're also mixing paste and concretes, but I really want to focus on the mortars for now. So the mortars that we'll be mixing will be mixed with type 1L cement, number 23 fine aggregate, and water. And then we'll also be creating 3 kinds of mixes. We're going to be using either carbon black or nanosilica at 0.5, 1, and 2% by weight of cementitious material, or no addition of nanomaterial. So that's going to be our reference sample. And we're going to create these mixes. So there's about 7 entire mixes that we'll be doing for this mortar. And each mix will have 20 samples with 2 by 2 dimensions in inches. Another thing to consider with the mix procedure is how we're going to incorporate our additives. Now for nanosilica, it's quite easy. All we have to do is add the concentration of nanosilica to the batch water, and then we're going to mix per ASTM C305. But for the carbon black, it's not as simple. Because it's hydrophobic, we have to analyze some different dispersion methods. So we tried 2 methods. Method A was the dry mix method, and method B was the high shear mixing method. The dry mix method simply required the concentration of carbon black being stirred in with the dry cement powder and then mixing. Whereas the high shear mix method, it required us to use the carbon black and adding that to the batch water and then high shear mixing it for about 90 seconds, at least 90 seconds. And what we found was that using method B resulted in less agglomerations, as you can see in those bottom 2 photos. And even some of those agglomerations that we might think are carbon black agglomerations are actually pores. So it was much more successful to evenly disperse the carbon black using method B. So we decided to use that method for all future mixes. And then an important part to address here is the curing process as well. So the methodology behind CO2 curing is we start off with a fresh mix sample. Under a tarp, it helps us retain some of that moisture and keep it at 100% relative to humidity so that the pores remain saturated. Then we're going to move it to a conditioning chamber where it allows us to release some of that water being in an environment at 50% relative humidity. And then we'll move our samples to a sample CO2 curing chamber. And this will be at 20% CO2 concentration. The optimal range is between 40 to 70% relative humidity. And that allows for some of our pores to have some pore water within them, but it's not completely saturated because we need some space for CO2 reaction to happen. And what happens is that CO2 reacts with some of the cement minerals and hydration products to create calcium carbonate, along with some other things. And this in turn results in a lining of our pores with calcium carbonate on them and a release of water as well. So to review the method that we've used, we're going to have our fresh stage, in mold curing at room temperature under a tarp. Then after 12 hours, we're going to move it to a conditioning stage in a curing chamber at 50% relative humidity. Then after that additional 12 hours, we're going to split our samples into 2 different groups, the normal curing group, which stays in that environmental chamber, and then the CO2 curing group, which moves on to the CO2 curing chamber. with a temperature of 60 degrees Celsius and a relative humidity of about 50 to 90%, depending on the samples that we're using. And then we're going to cure them until testing in open air conditions, which is about relative humidity of 30 to 40%. At room temperature, and then we're going to test these at different ages of 3, 7, and 28 days. The experiments that we're doing for our mortars, what I'll be showing to you is highlighted in bold. We're looking at 3 and 7 day compressive strength, but for future reference, we also have 28-day strength that we'll be evaluating, some SEM images, and some isothermal calorimetry results that we'll be analyzing in the future. So for our 3-day compression, what we found is that when looking at our reference material, which is shown on the left in orange, we can see that carbon black and nanosilica does help improve that 3-day compressive strength. The highest improvement is seen in the carbon black at 2%. However, what was interesting was that we're not necessarily seeing a linear increase in strength with our nanosilica samples. There's actually kind of a peak occurring with nanosilica at 1%. Furthermore, when we're looking at our CO2 cured samples, we're seeing that nanosilica actually kind of decrease our strength in reference to our reference sample. However, at 3 days, not nearly as much. Nanosilica at 1% still improves the strength. And then for our carbon black samples, we're seeing an overall increase in strength as well. So we can generally say that nanomaterials increase strength in standard and CO2 cured specimens. Generally, we're seeing about the same, if not a little bit higher, increase in strength. However, for a compressive strength of mortars at 7 days, we're seeing something a bit different. Compared to our reference, we're seeing that most of our carbon black samples can slightly increase the strength, except for our carbon black at 1, it's slightly lower at a negligible amount. But then for our nanosilica samples, we're seeing an apparent decrease in strength, which is surprising because in most nanosilica studies, we actually see an increase in strength, but this might be because of our curing conditions. And then for our CO2 cured samples, we're seeing that almost all of our nano-added specimens reduce the 7-day strength. The only one that exceeds the strength of the reference is carbon black at 2%. So we can say that carbon black at 0.5 and 2% does increase the strength, but nanomaterials generally decrease the strength, particularly in CO2 cured specimens. So to conclude, we're seeing that nanomaterials can improve early age strength development. Nanosilica can negatively affect the compressive strength in both standard and cured samples compared to the reference samples when we're looking at time as one of our variables. And we're also looking at the curing conditions. This can greatly influence the mechanical behavior. Particularly with our nanosilica samples, we're seeing a reduction in strength for some CO2 curing and some reference samples. So the curing conditions should really be evaluated, particularly for the nanosilica. So future experiments include some mortar analysis for SEM, 28-day compressive strength, and isothermal calorimetry, as mentioned earlier. For our paste, we want to evaluate the effectiveness of CO2 curing on the carbonation of our samples. So we're going to be using TGA, that's thermogravimetric analysis, SEM, scanning electron microscopy, and XRD, or X-ray diffraction, to see what really is going on in our samples. And then for concrete, we're going to be looking at compressive strength, formation factor, and the evaluation of transport properties, particularly for reinforced concrete specimens. We want to see how nanomaterials and CO2 curing influence those. However, further analysis is necessary for optimization and implementation, so we have to keep doing research on this and see just how well it works. Here are my references, and thank you all for listening. Thank you to the Velay Research Group, Purdue University Law School of Civil Engineering, TRANS-IPIC, and of course the US DOT for supporting this project. If you have any questions, please feel free to contact us via email. I can also take questions now, so thank you.
Thank you very much, Aniya. I would like to, we still got about 5 minutes, maybe even more. If somebody has a questions, please feel free to ask. Don't be shy.
I may have a question.
Yeah.
Good afternoon, everybody. That's a very nice presentation, and I can tell you I started to do this work sometimes in the past. And one of the comments I've been receiving when I put the concrete in a CO2 chamber for curing, the comments I got from some of the industrial members is that the carbonations with curing could expedite the corrosion of the steel rebars in concrete, and that becomes an issue if you were going to use this for steel reinforced concrete. Other things also, I'm glad that you tried the CO2 curing, but how I will scale this up when it comes down to curing large structure elements. I mean, this is a lab skill. I understand that we all have to start from somewhere. But consider in your research how you will scale this up. So it's just a comment to consider, but a concern you could consider looking at it. I have not had the chance to do it. Is this steel reinforcement? So that's my comment. Great work. Thank you.
Thank you. Yes, that's actually a great point. That's one of the reasons why we're looking at the formation factor, and hopefully in the future we're looking at chloride permeability and other factors that would influence the effects on that rebar. So that is a major concern. Professor Velay, if you'd like to.
Yes, I would like to add to that the first test that we did, I think was with XRD and also XRF. What we found out is that what is being carbonated during the CO2 curing is mainly the Velay, one of the anhydrated products, and it's not the calcium hydroxide mainly. So the fact that it's not calcium hydroxide, the main compound that is carbonated, it makes it reduces the, let's say, the risk of corrosion, in the sense that the fact what it makes for carbonation to be a problem for corrosion is because of the reduction of the pH due to the conversion of CH into calcium carbonate. However, in this case, with CO2 curing, we don't have that problem, or this is our hypothesis. We will test it, and we will do corrosion testing to see that indeed, because what is carbonated is not what it provides concrete with high pH, most likely we are not getting this reduction of the corrosion resistance, because we are not reducing pH, and therefore we will not be reducing, at least not in the same extent, the threshold of chloride to initiate the that's I think one point, but we will test it for sure, and we will see the results. So that's one of the things that we really want to do. And in terms of scale up, do you want to respond, Aniya, or do you want me to do that?
Just small input for the scalability of it. The precast industry, from what I've seen, it's actually meeting. Of course, there's a lot of research going into the scalability of precast elements, but precast elements are being used currently in especially a lot of hydro projects, so large dam outlets and things like that. So I think it's it could potentially be scalable. Of course, that's a lot of research that's in a completely different field, but scalability, of course, is something to pay attention to, and good that we're seeing that occur.
Yeah, I think the question was about the scalability or of the CO2 treatment, how we will do the CO2 treatment in precast element sites.
Yes, from what I've
talked
seen,
about,
yeah, there are some CO2 plants, which I'll have to get those references for you, but there are some CO2 plants that actually have a CO2 curing sort of standard that they themselves follow for their industries. I don't think it's necessarily standardized, so that is something to look into, but that's a great question, Professor Velay.
Yes, I agree. And as I said, there are other treatments in precast production that requires also chambers and other equipment, and either with vacuum bags or with the chambers itself that they use for other purposes, we can induce the CO2 curing. So, of course, that will be maybe second or third year if we are going in that direction. But I think that's something very feasible. But it's a very good point, and it's, I think, the
I don't know.
May I add just one quick comment? Aniya, great presentation and great work. As we were also impressed with your presentation at the workshops here. It seems that you're keep going in that direction. Very good work. Following up on the scalability, of course, one idea we have to keep in mind when we're working on these projects is always implementation. And I like the statement you had at one of your slides when you said there will be future work on scalability and implementation. So let's just keep this in mind. So it won't be a bad idea, for example, start early in your research, communicating with a precaster or two in your area. Get them involved, get their take on what you're doing and the practicality and their views of how this could be really implemented in the future. One thing I really think that would be exciting for them when you talk to them is the early strength that you are getting, even by a little bit, from the carbon black that you are adding. I know that at 3 days, it was more than what you have at 7 days. They love that because they are really, especially for the pre-stressed components, precast and pre-stressed. Now, you're really looking for how they can release the pre-stressing reinforcement as early as possible. So even if you have some data for 1 day or 48 hours, please present it to them and put it in your slides, and because they might get excited about that, even if the strength comes almost the same at 7 days or 14 days. At the early stage, the strength is very important, as well as maybe that's a follow-up question. Is there any plans for conducting any tests on the durability, the long-term behavior of these nano materials that you are adding or the curing process? Do you have any plan for that in the future?
Yes, we've discussed that actually, especially I know it was mentioned earlier in regards to corrosion for reinforced elements. That's one of the main things that we're looking at when it comes to long-term durability. But there are a few other tests that we're looking at. Of course, it's a lot of things that we're actually being surprised with. Water to cement ratio, as we've seen, in our project, we're looking at 2 different water to cement ratios, and we've seen completely different results for them, which introduces completely different durability concerns. So we're looking at a lot of things in regards to that. But yes, durability is one of the main things that we're looking at for this project.
Thank you.
Thank you. Yeah.
Thank you very much, everybody who asked the questions, and Aniya and Professor Velay for answering them. Are there any other comments or questions? If not,
Am I audible?
yeah, go ahead.
So I just have a quick question that you said that your project was regarding the curing the concrete. So is this a hot process curing? I mean, that is performed in a kiln chamber, or this is other kind of curing? I'm just being curious.
Yes, contrary to what we presented at the April workshop, what we're doing here is we're curing our samples at 60 degrees Celsius. So it's warmer than what we're used to, but I wouldn't necessarily say it's a hot kilning process, but it is warmer than the room temperature curing that we're looking at.
So these have to be performed in a particular chamber, or we can do it just in a particular room or any other room?
This is in a chamber. This is in a CO2 curing chamber. So it heats while they cure.
And also, do you need any pallet or something like that on which you will put your concretes? Or
I'm sorry, you say that again?
Like, do you need any pallet or any, any floor or a platform on which you will put your concretes, and after then you will send them into the curing chamber?
Oh, I see what you're saying. Most curing chambers, including the one we're using, has its own shelving units within them. So there's no need to roll pallets in and pull out. It's a shelving type unit, which is not what the large scale curing industry would be using, but this is just for experimentation.
Okay, and just a last question. On that shelf, can you put different types of concrete, or you can put just one concrete on each shelf?
Different types. The one we're using for mortars, but there are larger units. If you look some up, there are some larger units that can house, a closet full of CO2 specimens.
Okay, thank you.
No problem.
All right. Thank you very much. We'll move to the second presentation right now. The title of the presentation is Evaluating Scanning Technology for Process Monitoring and Quality Control in Precast Concrete Fabrications. And we actually have two presenters, if I understand correctly, Dr. Nahmens and Dr. Ikuma. Professor Nahmens is specializing in industrial engineering, process improvement and quality control with special emphasis on offsite construction and lean production techniques. And Dr. Ikuma is also a professor in industrial engineering who specializes in ergonomics, industrial and system engineering, applied, among others, to construction environments. So looking forward to that presentation. And I'm not sure which of the professors starts. I assume it's Professor Nahmens.
Yes. Good morning. Thank you. Thank you for the introduction. Just a little outline of what we're presenting today, just going over our objective, motivation for this project, approach that we're taking as far as the methodology, and our current status of the project, and we'll wrap up with next steps. Tyndall Corp is our partner on this project, sort of like our test bed for some of the ideas, and they are a precast concrete manufacturer, and they do support the transportation industry. So we're learning a lot about the different processes and quality control that they have in place. So just wanted to introduce them as well. As far as the objective of this project, what we're trying to do is kind of evaluate and propose an efficient way to do quality control using scanning technology. So really in the industry, we do see a lot of old methodologies in the sense of tape measures, and they're pretty intense on the workers, and they're sometimes not as accurate, right? So what we're trying to do is document the process, understand what the current process is, and then try to integrate more modern technologies into it. So the scanning technology is one of them. And hopefully with this, we can help find and, detect quality deficiencies early on so that we can, improve the process, improve the outcome of the product, make sure that anything that goes out of the manufacturing down to the field is going to work perfectly fine, and we're not going to have any issues in the field. So as far as the approach that we're taking, we have 3 stated questions. The first one is, what is the current process, right? So what is the current quality control process for precast components? How do we determine quality and check quality throughout the whole process? The second one is, where are the biggest issues in quality control that we're finding in the manufacturing precast components? So once we identify those issues, then we can see how state-of-the-art measurement tools like scanning tools, for instance, technology, could be integrated so that we avoid those issues. So where we are so far is basically trying to document the current quality control process. So overall, the current quality control process has 2 major steps: the pre-pour and then the post-pour check, if you will. The pre-pour, we have several checks that are performed, and I'll tell you more detail of the specific measurement or the specific characteristics that they're checking, but they prepare the form, they have a pre-check of the form, then they put all the elements that go into, then they have a pre-check of that. And then they have the pouring, and after the pouring, they have a pre-check as well. And in between those, if they do find any issues, obviously they check for those. After the pour, or right before the pour, they also do quality control or quality checks on the actual concrete itself. And those are sent to in-house lab to be tested. But the pre-pour checks, the characteristics that they're looking at, or the quality characteristics, it's basically dimensions, right? Length, width, depth, is it square? And then the proper alignment of the different embeds that go into each component, right? So that is something that they're checking currently. The concrete quality check is also performed. Your typical cylinders that they pour and they come and they bring them to the lab to test for different things, just to make sure they have the right quality of concrete going into each of the members. Here's a different, more visual picture of the pre-checks. So if you're looking at, how it's currently being measured, it's typical manual using a meter to tape measure to measure the length. From an operational perspective, it's taking 2 persons, so labor hours and so forth. But that's the current process. Then they check for any embeds, make sure they're positioned well and they're right, based on specs. And then they have their pour, their check as well. The post check or the post after they pour it, once they have, the element has been cured and it's moved to the yard, they have a post check, again, making sure that the pieces or the plates and so forth are in the right position. If they do have some issues, they will fix those. And then there's a second check, and then there's a visual inspection, just to make sure that they're getting a quality product. Post-check measurements, similar to the initial ones, the length, the width, the depth, the squareness, and then the location of each one of those. Again, similar to the pre-check, they're all done using a tape measure, very labor intensive, and relying on the expertise of the worker and, against the drawings and the specs of the project. So that's kind of the current process. Here are some more pictures on that. So looking at, the length and just the dimensions of it. Once they figure out what the dimensions are, if they do have some issues, they will, kind of label the part with a red dot if it's defective or needs to be fixed, or a green dot if it's good, and they check visually, all around the element just to make sure. So the process itself, it's pretty straightforward, pretty similar across industry and in some sense. You're going through your process, and then after each major step or major progress on your build, you check against your specs. So what we did was kind of collect some data to see what are the major defects, if you will, or quality issues that they were experiencing. And we try to split it up into pre and post pour, because those were the major checkpoints in their quality control process, just to identify. So you're going to see, and I'm going to go fairly quick on this, not much detail, but we focus on beams and columns, which are projects that will support, potentially support the transportation industry. But most of the result, and I'll give you a summary in a minute, but this is the by type of defect, if you will, of the pre-pour. Mostly is misalignment or missing elements, and that kind of mimics a little bit in the post-pour as well, that being the top type of quality issue. As far as item, plates and inserts, again, which kind of relates to the misalignment, tend to be the same, the ones that are the most frequent. So a summary of those defects that we've seen in the in both pre and post pour are, if we look at type of quality issue, is misalignment and missing items for both. So this is kind of giving us an idea on how can we use the scanning technology, or where in the quality control process we can maybe, add something or change the approach so that we can capture this. And as far as type of element, plates and insert are the top ones as well for both. So this is giving us, some ideas on how or what to change on how to improve the quality control process, so that the idea is to catch those mistakes early on so they don't happen throughout the process, so that we can minimize any quality issue. And how can we integrate scanning technology or more modern technology into that process as well. I'm going to pass it over to my colleague, Dr. Ikuma, who's going to kind of explain a little bit of that technology that I've been talking about.
Sure. So our next step was to look at what kinds of more modern technologies were available. And we mainly looked at products that are available from Faro. And I'll show you where they came out and did some demonstrations for us at Tyndall to show us some technologies. So the benefits of having these more modern technologies is that it can potentially eliminate human error. So where we saw that misalignment was the biggest quality control issue, then maybe that can help with detecting that misalignment at earlier stages. And it can also help us reduce time to perform those checks. So we saw that just anecdotal average time it takes to do those quality control checks is about 45 minutes per piece. And then we'll see that these modern technologies, again, just an estimated average time of more like 10 minutes per piece. So there could be some significant time savings there. And then we see that there's different scanning technologies available, and we feel like it can be applied to the transportation applications. So, next slide. So we looked at 4 styles of measurement technologies. So there's two basic classifications. So there's scanning technologies and then there's tracking technologies, and they can both get you to the same endpoint where you end up with a scanned model of the piece and you end up with dimensions. And the difference being on where the focus is. And so depending on the application, that can drive which of these products is most appropriate for use. So the first one is the Freestyle 2. This is the scanning technology. This is a handheld device that it takes 3D scans of objects. It's highly mobile. You can do real-time visualization. You scan and you can upload the scans to a computer, and it provides a nice 3D model of the object. What it doesn't do is calculate dimensions. So to do that, then you have to export or integrate with, say, a CAD program to get those dimensions. Okay, so that first one is Freestyle 2. Is a scanning technology. So the next one, the Vantage Laser Tracker. The tracker focuses more on getting dimensions. So it takes the real-time measurements by plotting points in the plane. So you can see there that it is using a laser to get those distances. So this one ends up being really a better choice for quality control. So it's real-time data acquisition, but it does not create scans of the whole part. So instead, you would start with dimensions. If you wanted to create a 3D scan, then that would require additional processing. This is a really easy product to use, is the other benefit. All right, so the third one is the scan arm. This one, we actually didn't see a demo of this one. It ended up being too detailed for our use and really for use in transportation industry, we feel. This one is, for one thing, has a smaller range. So the range is just 4 meters. So when we're talking about, say, bridge components, that's going to be too small in most cases to be useful. But it takes a really high detail scan, up to like the microns in terms of tolerance. So it can give you a really high level scan, and it's connects to your smartphone. It's the most accurate. But again, we felt like that one was maybe not as applicable for the transportation industry. And then the last one that we considered was the focus laser scanner. So this one is again, it's a scanning technology. So it's going to give you a 3D model in the end. It has a very large range. So this one's appropriate if you want to scan a whole building or say a whole bridge span, for instance. You could do that. It also has smartphone capability. It can connect to Wi-Fi. So again, this one's most appropriate for really large scale scans. So next slide. So here's just a comparison of those 4 products that were provided. Those were all with Ferro Technologies. So we see that those first 2, the Freestyle 2, which is a scanner, and then the Vantage laser tracker, were the ones that we felt were most appropriate for manufactured precast components. They can both be used in the field and at the fabrication stages. Right. Next slide. So Ferro came to Tyndall, the Tyndall plant in Mississippi, and we joined them there. They gave us a demonstration of these 2 products. And I have the Vantage laser tracker highlighted here because that's the one that we think is going to be most promising for Tyndall's applications. But just to go over a little more practical details for each of these. So the Freestyle 2, the scanner, is about $4,000 for the product. It does reduce the time that it takes to do a scan, to do the initial scan, I will say. The drawback there is that if Tyndall is interested in the quality control, to get the measurements, it takes more time to process that scan than to get the measurements. So that's kind of the downside. The upside is you get a really nice 3D object that you can use for comparisons, and then you can integrate that with CAD software. So this is a relatively new product. So when we asked about the lifespan, they weren't too sure about that. In comparison, the Vantage laser tracker is a tracking device again. So it's concerned more with the measurements. It is more expensive. You can see there with the prices for software, calibration. So there's different expenses involved on an annual basis. It also reduces the time it takes to get the measurements for a piece as opposed to the current method, which we estimate around 45 minutes. And you can also, so whereas the tracker focuses on measurements first, you can create a model using those points later. The lifespan of this product is 10 to 15 years. So even though it is a pretty hefty upfront cost, it does have a long life. Next slide. So we have those products to consider, and we wanted to think about, well, how does that fit into the quality control process? And can it help improve or reduce nonconformances? So thinking about where the laser tracker would fit in. So that's the one that we feel is going to be most useful for quality control checks. So the red arrows on the diagram here show where the process will change from the initial and the pre-pour check. So the first thing is that before the measurements can be taken, we have to upload a template into the software. So that comes in before you do anything. And then before you do any of the measurements, you just have to set up the laser tracker to be in the appropriate spot. So this one is, a little like having a video camera or a camera on a tripod. So you got to set it up in the right spot. And then you can perform all of those pre-check measurements. And then the software in that number 3 box will be used to perform an audit and to tell you whether you are within the specs or not, based on that template that was uploaded before we started. Next. And they have the same idea for the post-pour checks, where you would need to upload a template ahead of time into the software and then set up the tracker when you're ready to do the measurements. And then the software will be able to perform an audit compared to the template so that you can see where any problems might have occurred. All right, so next slide. And then we just have some pictures of the demonstration. This was the Freestyle 2, this was the scanner. And then, so the picture on the left is of actually taking the scans. You can see, if you notice on the ground, There's a white and black marker. That's the marker for collecting the measurements. And there were several of those markers placed around that T beam that we were scanning. And then on the right is just where we had uploaded the scan to the software. All right, next slide. And this was the demonstration of the laser tracker. So you can see, and again, it's just a relatively small device on a tripod. So it's easy to move it around. It's easy to use it either within the facility or you could take it out in the field. So next slide. And then this was the focus laser scanner. This is the one that you would use for much larger scales. So Farah told us that other companies have used it to scan, say, an entire manufacturing facility if they were wanting to look at material flows, for instance. Next slide. So you might be wondering if Farah is the only company in the game, and they're not. So we looked at some other companies that also produce the scanning and tracking technologies. It seems like we hit a nice balance with Farah in terms of price versus capabilities. So you'll see with these links here, there are some other companies out there doing these things. So the Leica Geosystem is pricier, but it's also really fast. Whereas the API brand is cheaper, but it requires more back-end work. So, and then the Keyence is just limited outside of doing two-dimensional inspections. So depending on your needs and budget, obviously, some of these might be more or less appropriate. So going back to our original question. So we looked at what the current QC process was for precast components. It involves a lot of manual measurements. Takes about 45 minutes per piece, and that's just to get the measurements. And we looked at where the biggest issues were in quality control when we're manufacturing those precast components. It really comes down to misalignment. So it has to do with tolerances being off. So we wanted to see, can these state-of-the-art measurement tools assist with quality control, specifically looking at those the misaligned parts. So if you'll go to the next slide, please. Actually, if you'll go on one more ahead. Yeah, so what I want to talk about is how the laser tracking could show some initial benefits. So because the laser tracking technologies have the ability to be more precise than the tape measure measurements and also to eliminate human error in getting those measurements, we proposed that we could get earlier detection of proper locations. So maybe catching more of those misaligned parts at the pre-pour check rather than letting it get to the post-pour check before we realize that something needs to be adjusted. There's the time savings, and that's the other big thing, is trying to reduce the time savings. So when we think about future steps, we want to, in our next steps in this research, really validate whether those items that we're proposing would help with QC actually play out. So we'll be introducing the scanning tech to the QC team at Tyndall. They've seen it, they've seen the demos, they're excited about it, but we want to get some real data. So perform some mock QC inspections on products that they already have, and validate in terms of economic comparisons. So there's going to be some savings if we can save time, but then there's also going to be big savings if we can reduce the rework based on fixing those quality control processes. And then of course, customer satisfaction, if we can get the right products to the field and, and eliminating that rework. So that also reduces the time, the turnaround time as well. So Lisa, if you can skip to that last slide. Yep.
All right. Thank you very much, Professor
Thank you.
Ikuma, Professor Nahmens. Very interesting work. we will open the floor to question. I will ask the first question, if I may. I was wondering if that technology can actually be used for inspection of installed precast elements, because very often, there might be some misalignments or improper installation of girders, let's say in the bridges and so forth. Would the same principles be useful for inspection of the actual constructed structures?
Yes, absolutely. So both of those, both the freestyle scanner and the tracker they're easy to take into the field, but yes, you'd be able to scan the pre-existing in place products. And in that case, the scanner might actually be a better choice than the tracker, because you could get that 3D image to start with, and then you could go back and calculate the dimensions. And it'll allow you to look at things like the squareness, the twist, based on those scans.
Well, it's sort of a follow-up question. If you do pre-production inspection, and if you make an adjustment, I wonder, why do you need to do post-production inspection? Wouldn't it be just a simple matter of visually checking whether the form was not completely filled, but otherwise, why do you need to measure the dimension? Unless you are assuming that during the production, the formwork is not holding.
I think what you said is the reason, is just to have that secondary check. Because
it seems to me like you would be able to save a lot of time and effort if you ensure that once I check that pre-construction, I secure everything in place, and that that will hold. The other thing that struck me in the data that you were showing is that the errors in terms of reinforcement placement were very low, like 4% or something like that. Where I thought that would be a much bigger problem, considering some of the intricacies. Sometimes you have multi-layer reinforcement and so forth, but that doesn't seem to be the case. Okay. Well, any other questions from anybody else?
Yes, I have a question.
Go ahead, Dulcie.
So thank you very much for the presentation. Since one of the Purdue teams is working in a similar area, we are really excited, and we hope that our groups can kind of collaborate. So you mentioned that Tyndall is your industry partner, the precast manufacturing partner. I believe that Tyndall is kind of one of the more advanced precast manufacturers, and their systems are a lot more automated, probably, than some of the typical precast manufacturers who supply products for the transportation industry. So my question is, when you were collecting the data related to current QC tools that are being used, the products at Tyndall, are they primarily, customized elements, products, or are they bulk elements which are provided for specific parts of the transportation industry?
So they do have projects that support the transportation, like parking lots, for instance, and things like that, if you account that as part of it, the infrastructure, if you will. But their projects seem to be very custom and unique to their customers.
Okay. So the point is, so the setup time for using the scanner and the tracker, how does that vary when you have, customizable products and kind of what I would call bulk products? What is the setup time for, different groups of elements?
That's actually one of our questions. So in the demo, they just showed us how to use the technology.
Yeah.
But we didn't actually upload, an initial plan. But that's part of our next step, is to see how much time there is there
to set it up, right? Because, we had a chance, our Purdue group had a chance to visit a precast manufacturer in Ohio. And I mean, I would say all of their QC methods are very manual. So they haven't used any levels of sensing the way, you have described. And one of the points that the QC team shared with us is that the level of training that their workers have is not very sophisticated. So whatever tools we are hoping to introduce for QC have to be easy to use, easy for the workers to use, and I mean easy setup time, and so on. So that was a point that I wanted to see whether you had something similar during your interactions with the QC team at Tyndall, because Tyndall is a lot more advanced than many other precast manufacturers in the US.
Yeah, so I'm not sure about their current training on their methods, but Faro does, as part of their package, they have like either 2 or 3 day trainings with their products, and some of it is offsite, and then some of it's on-site too.
And the data that they get, when you're using the Freestyle 2 as well as the Vantage laser tracker, I mean, where's the processing being done? Is it all in real time, or is there some lag between when the data is collected and when you get the results?
There's a slight lag in just however long it takes your computer to do the processing.
Oh, okay.
So you can export the data like directly to a computer, and it processes it right there.
Okay. Thank you.
Thank you. Any other comments or questions from anybody else?
Well, I have maybe a comment. Isa and Laura, thank you so much for the great presentation. It's really important topic. Your research is one of the projects that the TRANS-IPIC Center is supporting that's close or closer to the implementation stage, which is exciting. Of course, we have a very wide portfolio of projects. Your project is one of the closer ones to the implementation. And it seems that you are keeping your eyes on that, target, which is the implementation, which is very good. And that brings me to the, comment maybe following up on what Dulce was saying regarding Tyndall. Tyndall is known for their, of course, they're great precasters, but they're not per se transportation related precasters. And the reason I'm saying that is that, a lot of the technologies you're really investigating, these could be applied anywhere with any precast component, whether in buildings or in bridges, for example. But when it comes to the details like the alignment issues that you referred to, you will start noticing, and you can maybe speak to other precasters from the transportation industry, and they will maybe shed more light on this, that they have their own unique set of problems when it comes to installation of their components, like bridge girders on piers, for example, on column caps, for example. Now the ABC, the accelerated bridge construction technology, is really thriving, and everybody's talking about it. So one big factor that governs this ABC is the joints between the components, whether we're talking about the pier and the footing, or the girder and the pier cap. And especially with the existence of precast, pre-stressing, whether it's post-tensioning, pre-tensioning, that becomes its own set of problems that industry faces when it comes to transportation. So it would be exciting in the future to see also that in addition to Tyndall, you start expanding your portfolio of precasters to collect more information, and when you especially come to the phase of actual implementation, to use data from the transportation industry. It will be very, very important for the success and the application of the technology that you are studying in the transportation domain. But congratulations on your great work, and I wish you continued success.
Thank you.
Thank you very much, Bassam. I think we arrived at the time where we're supposed to finish. So thank you very much, everybody, for participating, especially the presenters. And we will be looking forward for the announcement from Chris about the next webinar in July, correct?
Yep. You should see something probably in the next week or so.
All right. Well, I wish you a good rest of the day, and until next time then.
Great. Thanks, everybody.
Bye-bye.
Can't go.